Greetings, sir. We are Group 6. Our mission is to modernize Malaysia's logistics by solving a critical national challenge, the failure of standard sensing during our intense monsoon rains and haze. To ensure pedestrian safety and achieve millimeter precision mapping, we are implementing solid-state LiDAR. This remote sensing technology uses a rapid laser pulses to build a dynamic 3D point cloud in real time. Unlike radar or sonar, LiDAR's light wave provide the superior resolutions needed for our robots to feel their surroundings and navigate safely through any storm.
Use of LiDAR. A car identifies a physical distance with the support of optical technology in LiDAR system, and it bases on the time of flight principle where interval between emitting and returning a light pulse is measured. Time of flight physics. D equals ct over 2. The speed of the light pulse covers the rounded distance of 2d, and thus the time measured t has to be divided by half to find the real distance of the object. How can a car see distance? Well, the car releases a short burst of laser light which usually in the form of infrared light which cannot be seen by a human eye. The timing must be precise and it will count as emitting a pulse. When the pulse reaches an object or pedestrian, the backscattering will be very partial. The photons that reflected into vehicle are detected by photo detector mounted on the car, and the clock is stopped and the computer uses the above equation d equals c over 2 to measure distance of light. That's all from me. Thank you.
Now let's look at the fog problem. Fog contains microscopic water droplets that block the LiDAR laser propagation by the process called scattering. The key factor here is the position of laser in fog depends on the relationship of laser wavelength and fog droplets. Shorter wavelength, like the visible blue or green light, will strongly scatter, causing faint returns and fast weakening of a signal, and it's not possible to reach long distance. Longer wavelengths, such as infrared and red spectrum, have less interaction with the droplets, hence allowing further distance into the atmosphere to be covered before the energy within them is lost.
After knowing what is a LiDAR system, let's talk about the problem in traditional LiDAR system. Traditional mechanical LiDAR relies on spinning mirrors and lasers. While effective, these bucket-style sensors are bulky and highly susceptible to mechanical wear and misalignment caused by the environmental privation. So, for our solid-state design, it eliminates these risks by using optical phase arrays and non-local metal surface. By leveraging constructive interference nano emitters on a silicon substrate, we can steer light beams electronically rather than mechanically. So, this flat-length approach results in a significantly smaller, lower power sensor, perfect for precision needs of autonomous delivery robots. Furthermore, removing moving parts ensures high reliability in humid or high vibration urban environments in Malaysia. So ultimately, we are replacing limited motor speeds with nearly instantaneous scanning. This transition from mechanical to all electronic architecture provides a more durable, integrated, and precise solution for the future of navigation.
About eye safety and range optimization. Now we want the laser to have more range, and that means more power. But doesn't that mean that it will damage our eye? Not quite. This is where the 1550 nanometer wavelength comes in, because compared to the conventional ones, which is 905 nanometer, this specific wavelength will not damage our eye because it doesn't reach the sensitive part of our eye, which is the retina. And therefore, that means we can build as much power as we want on the laser without worrying about damaging the human vision.
Our engineering strategy is defined by a rigorous comparison between the 905 and 1550 nanometer standards. While 905 nanometer system utilize low-cost silicon photodetectors, they often struggle with atmospheric attenuation in high humidity. We have prioritized the 1550 nanometer regime to overcome the fog problem, as these wavelengths suffer significantly less from scattering. This allows for a higher photon budget, enabling a detection range exceeding 1 km and the dense point cloud required for high-speed navigation. Although it requires specialized in-gas detectors, this choice ensures the reliability required for our national infrastructure.
Think of our OPL LiDAR as a digital eye for machines. Unlike old LiDARs that use a spinning mirror, this is a solid state, which means there are no moving parts. By precisely controlling the timing of tiny lasers on a chip, it steers a beam across a room using light interference instead of physical motion. It's smaller, faster, and cheaper to build, and they are still improving the signals, but soon it will be the big brain behind how autonomous vehicle and drone safely navigate Earth. Traditional LiDAR like the 905 or the 1550 nanometer version usually relies on spinning mechanical parts to see. This makes them bulkier and slower. While the 1550 version has the best range and eye safety, it's also the pricey one. Now, the game changer, the OPL LiDAR. It's all electronics with no moving parts. This makes them incredibly fast, compact, and durable. Once massively produced, it will be likely the cheapest version, yet the most reliable way for robots and cars to see our world.